Good afternoon, everyone. For those of you whose this is your first time, you may not know me. I'm Van Howell. I'm the CIO for South Plains College and co-PI on this National Science Foundation grant for BRICS, Texas. I've invited Dr. Sill to do a presentation today about his Raspberry Pi clusters that he's using to teach high performance computing. And I was also hoping he could talk a little bit about his repasses cluster that's just been set up or is in the process of being set up. Alan, the floor is yours.
Okay, so let's just go ahead. All right, so this is just some basic points of philosophy. I think that students learn best when basically you get out of their way, when they have control over the equipment, software, resources that they're using. We used to routinely wait till the faculty members went home when I was a physics major to rebuild the experiment so it would come out better, and it usually did. So I teach everybody that works with me, keep the senior faculty away from the equipment, right? And that this is a general rule that stood me in good stead for when I was from an undergraduate to now when I are one, right? The second thing is that on the other hand, high performance computers such as we use at scale in all sorts of things now are very expensive, and people have to learn somewhere. The fortunate thing is the basic ideas of building clusters of computers can be scaled down to even very tiny ones, even smaller than the ones that I've shown here. And we'll talk about that. So the basic concepts are scalable. And the nice thing about getting down to the point where the hardware is inexpensive enough that you don't care if the smoke comes out is that you can give people root access. You teach them about firewalls and to keep the stuff off the campus network, but you can let them be root, and that comes with lots of consequences and restrictions, which work much better at small scale than at very large scale. Learning, in my view, can't happen unless we can mitigate some of the things that I just talked about, the root restrictions that keep us from giving undergraduates, the root password to our clusters. So we want to create those conditions. And so I think that single board computers are a gift from heaven in this regard. And let's go on. All right, so the original idea, and I'm going to show you some links in a second. I encourage you to just search for this YouTube channel, Life of Raspberry Pi. It's at Life of Raspberry Pi on YouTube. It's got a 2 at the end, so at Life of Raspberry Pi 2. This was a little project that we got started with one of our master's students. We were trying to basically add more temperature measurement to our machine rooms at the High Performance Computing Center here. And I got tired of paying a few $100 per sensor, but these, they know you're putting it in a machine room, that gets very expensive. So I thought, look, these little home automation things are out. Let's get some temperature sensors. Let's get a lot of them, and we'll start wiring them up to Raspberry Pis. And we started with the Raspberry Pi 4B, I think it was. And very quickly, we started figuring out that you could put more than one Raspberry Pi together, and then that you could build little clusters of them so that you could have some fault tolerance and so forth. And that led us to explore a whole generation of Raspberry Pi cluster boards and related things. So next slide, we'll show you some links. So I encourage you again to look these things up. It starts with the monitoring project, and if you were to click on the no, we'd have to watch the videos, but I'll let you do it on your own. And these are a lot of fun. This is just Manoj's doing his first. I'm going to be a internet influencer, and it came out well, I think. But very quickly we started, just as I say, getting sidetracked into what can we do with all these single board clusters? and he delivered three in that series, and there's others on his channel that you find them, but that was the beginnings of this project. Next slide. All right, so then I found that I could put Fedora, the latest version of that time was 39. I could put it right on to a Raspberry Pi, and for reasons I'll explain in a minute, I'm not really happy with the ecosystem of software that surrounds these single board computers. It's very fiddly. It's very hobbyist oriented, and it doesn't really work like clusters work in your machine room. You could never get anything done we're doing a maintenance right now, and we've got 750 nodes that we're doing BIOS and firmware updates on. And we're not going to go plug a USB cable in and put it into flash mode for every one of those things, right? It's just not going to happen. So I was pretty unhappy with that ecosystem. And when I found that we could actually put enterprise Linux, whether your favorite is Red Hat or Rocky, we use Rocky Linux, and I found that we could start to automate this process. You can even PXE boot them. But what this is sitting on, and I'll show you a bit more in a second, and we claimed that supercomputing is the smallest cluster at Supercomputing 23. It was certainly the smallest one running enterprise Linux. And at that point, we were running, Rocky Linux provisioned in the same way that I would provision a cluster. So with the exception that each one of these nodes you'd have to put into a flash mode and so forth. So we got partway there with the enterprise Linux software, and we got started exploring others. We found dedicated cluster boards from a variety of folks. Let's go to the next slide. And these cluster boards speed assembly. So on the left is an SIP, weird name, Lychee Pi Cluster 4A. And I don't know who's in charge of the English naming of this, but it arrived with a nice little case. I'm actually showing two cases, front and back, on this left picture, and a Chinese spec power supply that was a little bit smaller than the US spec one, so we couldn't just swap it in. So the next picture, we took it out and we stuck it in an acrylic case with a US spec power supply. And this is kind of the beginning of our wandering into rebuilding these things. On the right side is a little closer view of that Turing Pi 2.5 cluster board. Both these cluster boards, the one on the left takes 7 cards, and the one on the right takes 4. And they are these SO-DIMMs. It's like an old-fashioned DIMM memory slot, but they're becoming popular for putting little, they call them compute modules. So in this case, what's a cluster board? A cluster board is a place to plug in these compute modules, which are the computer, but you leave off all the other stuff. You leave off all the Ethernet interfaces and USB interfaces. You just do that over a bus. The carrier card does that for you, and that cluster board carrier card interface takes care of the onboard Ethernet, and it's a little cluster, and you can do cluster things with it, like have a baseboard management controller. Well, baseboard management controller is nice because you can talk to this and you can kind of automate the provisioning thing that I was talking about. But we did find that this was, at one time an advance. Oops, looks like I got to switch audio devices. Hang on a second. Oh no, they're still okay. And at the second, in this second instance, they were actually kind of a problem because their design choices kind of limited us. So let's go on. So what are the disadvantages of these things? The operating system choices, when you get into these kind of custom hardware, we're no longer generally in the territory where you can make arbitrary choices. Certainly not for the baseboard management controller, though I did get control over the worker nodes. A lot of non-standard hardware and connectors. As I said, the boards usually provide require some special provisioning set up. Only certain versions of code were supported because it's really kind of custom hardware. They can't be bulk provisioned. And once you start adding up all the little things you add on, fan controllers and so forth, it costs add up. So it's hard to imagine scaling, these cluster boards to large numbers of them. And as a consequence, they become kind of a interesting little side road, but really hard to make a one-on-one connection to HPC methods, which are much more easily scaled from small numbers to large numbers sort of uniformly. And you end up treating more the special conditions of the cluster board than the idea of clusters. So, I'm a physicist, and we have this problem that, we do lecture demonstrations and we think that demonstrates physics, but what it really demonstrates is that you can only do physics with physics lecture demonstration equipment. And so you have to get away from that and teach people to find it in the real world. And that's the same situation we found ourselves in here. This is fun and interesting and it works, but it's not what we're after. So let's go on. So there's nothing wrong with alternate architectures. We started looking for things that would be much more of a direct analog of what's going on in the machine room. I mean, let's be clear. The Raspberry Pis are ARM processors. The SIP things I show you are RISC, and those are both making inroads. But we wanted to sort of go fast and simplify. And so I found a company called RADXA, and they made a thing called X2L. I'll show you these in a second, with an Intel Celeron chip and a real BIOS, and it can PXE boot. And I started building clusters out of these things. First, just one node, and then a few nodes, and pretty soon my desktop got overwhelmed. If you were videoing with me during that time period, you'd look over my shoulder, and I'd have a whole bunch of these things like I disassembled, much to the distraction of many an IT division management meeting, especially when I would get the screwdriver out while they're talking. Yeah, very distracting in the meeting. So I wanted to simplify, and I explored using power over Ethernet to simplify the power provisioning and get around another problem, which is when I give up the cluster board, I give up all the controls that cluster board had for remotely powering on and off the nodes. So if I put in power over Ethernet with a web interface, I can do that too. So that was, and then eventually we added, I'll show you later, a more advanced model, a little more compact called RADSA X4 with a more advanced processor, an Intel N100. So let's go on. Yeah, so this is a RADSA X2L. The right-hand side is in the box. I'm just taking it out of the box, and then next to it, up just above there, is the fan. And then on the left, you get a diagram of the front and back of the card. And these have like a lot of useful features, like it's got an M.2 connector to plug in a little NVMe drive. It's got onboard Ethernet and HDMI and power buttons and fan headers. Oh, and it's even got this little RP2040. That's a little Raspberry Pi chip just sort of stuck on the board there. You can talk to from the main processor, which again is a Celeron. And that purpose of that RP2040 is to talk to that GPIO header. Remember, we were looking in Raspberry Pis originally because we wanted to do temperature control. So all of a sudden I've got that back. I can use these things for everything I was going to use Raspberry Pis for. Only it's an x86 processor, and I can just, load it up and go. I don't have to get into fancy, stand in a certain pose and stick the USB cable in and push a button and hold and so, this is, where I wanted to go. Next. So I started building little clusters, these just stacked them together with little brass standoffs. You can buy these things. And look at the right, there's that case that SIP'd motherboard came in that we couldn't use the power supply. And I just stuck this thing in there and a power strip. And lo and behold, I have a portable 4-node x86 cluster that I can install Rocky Linux and Werewolf and Slurm and SPAC and all the standard high performance computing tools, standard scientific software, and run it with exactly the same software stack that we would run on our main clusters. So this is starting to get somewhere, but also pretty non-replicable. So let's go on. So we started. We had some Raspberry Pi acrylic shelves that we had bought from. We were thinking we were going to do this with Raspberry Pis. They weren't quite wide enough, so we extended them with plastic shelves. And I built this kind of not horribly ugly, but not terribly pretty, but functional stack of them. So the same thing as before, instead of brass standoffs, I've just got this little acrylic rack set of shelves. And then you see on the left a little close-up view of, we actually couldn't find any power over Ethernet to the 12 volt USB-C power delivery, very specific power connector that these things had. It had to be 12 volt PD, and we could, that's what those power supplies were in the previous drawing. I didn't want to use them, I wanted to use power Ethernet. So finally we had the idea that we could buy 12 volt power Ethernet splitters that had barrel connectors on them, and I won't go into the details, but we managed to figure out how to wire them up to automotive USB-C adapters. That was our way of getting on. And it worked, but it wasn't so pretty. So next. All right, so let's talk briefly about the RADS X4. Those were X2Ls. This is now a faster processor, an Intel N100 quad-core processor with a variable amount of memory. The price on these things depend on how much memory and whether you want an onboard eMMC, it's like a little built-in flash drive, or if you want to have an NVMe slot. And these things have both options. And Ethernet, 2.5 gigabit per second Ethernet instead of gigabit on the other ones. Some very fast USB 3.2 ports, and so you can add on other cards, a variable amount of memory. And they're all Power Ethernet friendly because this time they actually have a Power Ethernet header, which you can buy a little. There's a term that you run into in single board computers called the hardware attached on top. It has a really clever, a lot of people nodding, you've heard of these, it's like they call them hats. So a Power Ethernet hat, you can stick one on there and you can just plug it directly into your Power Ethernet switch. So that's a nice option too. These cost more. And the 2.5 gigabit per second, the better processor. And there's always availability things. So at various times we can get our hands on X2Ls and various times we get our hands on X4s. Next. All right, so we actually built a 20 node cluster of these RADS X4s. I've got 5 of them shoved in each shelf. They fit perfectly into this little 10-inch rack audio case that I had bought early on and set aside because I didn't know. It turned out to be bigger than I thought, and I didn't think I'd use it. But I found that I can get exactly 5 perfectly in these things, and I hooked it up to a nice switch. And Sam had the idea of entering the single board cluster competition. I'm not sure whose idea it was. There were several people involved, and they won second place overall this year, just a couple months ago in the SBCC.io. That's only second year that they've run this. There is actually a thing called the single board cluster competition. So this whole idea is getting popular. I encourage you to go look at SBCC.io for way more ideas than I have time to show you on how to put single board clusters together. So we're not the only ones doing this, but we got actually first place in the HP LinPack rankings. Again, these and the X2L clusters are provisioned with exactly the same software. I'm not talking about approximately the same. We pixie boot and we provision them with Werewolf. They're stateless. There's no disks. There's no eMMC or NVMe drive in any of these worker nodes. They're all statelessly provisioned from the head node, which is the thing on the bottom shelf there. That's a slightly bigger thing called an X4L. It just is an X4 with a bigger board that looks a lot like an X2L board. And it's also got 2.5 gigabit per second Ethernet and the ability to plug in bigger NVMe drives. So it's got a 2 terabyte NVMe drive. That's the only storage in this whole cluster. Everything else is statelessly provisioned by Werewolf, just like you'd provision a real cluster. So now we're cooking with gas. Not only does this thing perform well, it's cheap, Well, this is the most expensive thing we built. I'd say something like $3,500, something like that, all in, including me not knowing about the then available de minimis option, so I had to pay tariffs on it. Okay, next slide. Okay, so now we started to see, okay, how about we build a lot of them? And we couldn't go too overboard. They did have a limited budget, but we ordered parts and we started building them like I show you on the right here. It's a steel case from a hobbyist company. It's actually built for Raspberry Pi like boards, though it's slightly larger than Raspberry Pis. And we've stuck some DIN rail on it. I'll talk about more about DIN rail in a minute. And we've stuck a GPU on it, and I've got 4 nodes here. One is the head node. You can tell the head node because it's got one extra USB to Ethernet adapter on it. And then there's the power over Ethernet adapter. And now we've been able to buy commercial PoE adapters. We don't have to do any more rewiring of automotive adapters. You can actually buy them now that have the right specs. Okay, Jetson or Nano GPU, I'll say more about that in a minute. So this is one head node and 3 worker nodes, X2Ls. It's really built for economy. The GPU stuck on top was because they dropped the price on those Jetson or Nanos to $250, and that just seemed like a screaming deal to me. So we stuck a bunch on there. Next. So the thing about this is that I'm no longer building these things. My desk is clear, and the students built them. And they get together and they exchange notes, and they just built those last 3. Dr. Mengel is still waiting for hers. That her graduate student hasn't given up because he's using this as an example for the others. And the next slide. And I had one more slide of people. I'm sorry. Uh, these are the X4s that I mentioned, and I decided to build kind of like the ultimate small version of this, not the 20 node thing, not the X2L based thing. I was going to build kind of the best version that I could think of. And we gave it to one of our postdocs who's working on the REPAX project. So this is now, I've got 4 of these RADS X4s. I've turned them on the side, and I've got you know what a DIN rail is? If you open an electric cabinet, there's often a rail in the back of it that you clip various circuit breakers and things on. Well, you can just buy this stuff, and it's not quite as flexible as as adaptable as you might think, but you can buy lots of things that just clip right on it, including an adapter for a Jetson or a Nano GPU card. And so I bought some of these clips that clipped on 4 of these, clipped on the Jetson or Nano, and I stuck one of these X4Ls on top as the head node. And so it's all power over Ethernet except the Aura Nano, which has its own individual power supply. You can do power over Ethernet in those. I just ran out of PoE ports on this switch. So here we have a 4-node plus a head node plus a GPU node. And it's a little bit bigger than a Kleenex box. It's well, 2 of my small Kleenex boxes here. So it just sits on your desk and costs about $1,000, and it can do everything. All right, sorry, I had to switch headsets there. My long day of meetings and let's screw up. All right, let's go on to the last slides here. So what we've done is basically use single board computers and assemble them into clusters to teach HPC concepts. And we've done it a number of different ways. I didn't really have time to go back into, we actually did put those BRICCS-TX processors in use. We actually have several other classes of processors that I've talked about that are in the cluster board category that we're still working with. And there's a particularly clever box called a Mixtile, which actually has a PCIe fabric, which, the one thing you'll notice is that these little clusters don't have a fast fabric. We're just using the Ethernet for everything. We can use 1 gigabit or 2.5 gigabit. But this mixed tile clusters, they come in a really nice case pre-assembled. They're pretty expensive, and they have this PCIe fabric. So what we're using these for is basically comparison tests. And some students have gotten their degrees doing performance comparisons in the different architectures. Uh, the, the clusters I've shown you are basically aimed at this HPC education task. What's the simplest thing we can put together that performs just like a real cluster that you can, if you learn on it, you can actually run a cluster. And that's what I've showed you. I tried to strip out anything that's peripheral to that. So even though these cluster boards are nice, I wanted to focus on just take a set of nodes, give each a task, provide some storage, do a network, think about your firewall, your what you're going to connect to the network. Only the head node of these clusters ever connects to the campus network. Everything else is private network. And we provision them as exactly the same way. And I tell people I'd much rather you learn on a few $100s or a few $1,000s worth of hardware rather than a few $1,000,000 worth of hardware. And more to the point, not everybody can afford a few $1,000,000 for the hardware. So I think this is a very cost-effective solution. I will add here a disclaimer. People say, well, when are you going to write this up and start running workshops? And that was never my goal. I think that's a very admirable goal. I will support anyone who wants to take on that goal. I will pass on everything we learned. You probably can figure out how to do it better. The whole point of what we tried to do is to make it highly reproducible by stripping out the peripheral stuff. There's no secret sauce. We've just found kind of the minimum path through to build clusters. And I think everybody should do that, and we should try to get that into the classroom. Whether I'm the one to do it or not is kind of not part of the equation here. I'm happy to support it, but I kind of have a day job. And so the last slide, I think, is mostly just some references. Yes, so Sam actually wrote all this up at the PERC conference in 2024, did a poster and a paper from that. I give you some links to some of the parts. If you really want those cluster boards, it's where to get them. If you want to do temperature measurement, we found that you could stick actually dozens of these one-wire temperature sensors. I didn't explain one wire, but it means every sensor has an address and you can just string them together. You can have lots and lots of temperature sensors out of one board. And ask for other links if you're interested. But the RADSA stuff, I think you can just look up. I didn't put links in there, but you can find them, I think. And modulo tariffs, everything we've described is something you can do. So I'll stop there and see if there are any questions. Oh, and thanks to all the students and the postdocs who helped with all this, because I definitely did not do all of this myself.
So in comparison to a real cluster, how fast are they?
Well, that's a really good question. I should probably let Sam answer that question. He's done the benchmarks. Sam, are you online?
Hi, Dr. Sill. We I think Daniel is probably better placed for the benchmarks comparison. I think it was maybe 22 gigaflops, but yeah, I think that's just for the HP Pack benchmark comparison. And that was for the 20 node RADSCA X4 cluster. So we had about 22 gigaflops for I think each node.
Yeah, so thank you, Sam. So, HP LinPack results, we make a lot of hand waving and smoke around it, but you can calculate it, right? You just take the clock frequency times the number of cores times the number of instructions per clock cycle, and that's your flops rating. So we have 20 times 4 cores, and I think they were running. What speed were you able to get to stay within the power limits? It was about 2 gigahertz, something like that.
No, we didn't really. I think we just stayed within the power limits of about 250 watts.
Yeah.
So we didn't touch the speed.
Okay. Yeah, so these have a maximum turbo speed of the X4s have can go up to 3.4, but I think their nominal speed is like 2.2 gigahertz. So you just take 80 cores times 2.2 gigahertz times this is an Alder Lake generation, so I'd have to look up how many instructions per cycle there are there, and that's your flops rating. Of course, real world is some percentage of that. A good number is like 85% of that. So uh, we did it partly just to see if we could, would we run into any limitations? And we didn't really. And there is, I would say, a qualitative difference. When you're running on the 20 node cluster, it feels like a real cluster. The little ones, they're pretty little. 3 worker nodes, 4 worker nodes, depending on which one you're talking about. That's pretty little. It's enough to prove the concepts. But when you get 20 in front of you, you say, okay, I see. You can just keep doing this forever. You just have to pay attention to your network, your bandwidth to storage, other things, power limits. This SBCC.io had a 250 watt power limit, which I don't think we can see the power meter in the picture, but we had to have a power meter with a video camera on it all the time.
So do they generate a lot of heat?
No, not really. 250 watts isn't much. Probably your desktop computer that puts out that much, right? No. Though when my older son was living at home, his room was always distinctly warmer than the rest of the house because of his GPU cards. I'm personally most curious about what we're going to get right at the top of that stack in the middle picture. You can see that one of those little Jetson or Nanos. That's a little chunk of an Ampere uh, sort of an A100 class card. It's just like I don't know, like a 20th of an A100 or something. But it's still enough to do a lot of very decent stuff. It'd probably do quite a decent large language model for the smaller uh, iterations of it, for the small versions of it. And a lot of stuff you can do and that's $250, right? So, and plus, you mentioned heat. These things, there's not enough heat to even detect this little 4 node ones. I think the warmest thing in there is the Ethernet switch, the power over Ethernet switch, which does get pretty warm. Anyway, I'm excited about these things. I think we should do something. Right now, it's not a great time to do stuff with imported parts. Just wait a bit, The idea is there. And by the way, I did mention that you can go even smaller than this. You can take, you saw the little Raspberry Pi 2040 chip. There are lots of things in that class, little, Arduino class things that with a certain amount of work, you could actually get the same conditions. You'd have to use a really stripped down version of an enterprise Linux operating system, but you can actually get it on one of those chips. You could make a little matchbox size node and a few of those that'd be even smaller than what we talked about. I think this is a nice compromise because um, they're big enough to do something useful. The complexity you want to exercise is how do you provision multiple nodes? How do we can actually do MPI calculations on this. We can do OpenMP. We can, they're multi-core. It's not like 4 cards with 1 core per card. That would be boring. So there's just enough that even on the little ones that you can do a fair bit of work on them. And I'm most curious to see what they're going to make of these GPUs that we've given them.
So the competition that you mentioned, is that available to undergrad as well?
It's only available to undergrads. All these graduate students you see here, and in the picture that I didn't get into the slide set, I apologize to the people who sent me the pictures. It is in the latest version of it, but they couldn't enter. All they could do is advise the undergraduates. They couldn't even advise them directly during the competition. They had to do it ahead of time. So I was so proud of them. They were holding classes for these undergraduates. I'd walk in on them and they'd be busy explaining stuff. wow, man, this education stuff, it's really the bee's knees. It's great. Anyway, I really want to thank everybody who indulged, participated, contributed to this. It was a lot of fun. And let's see if you give me back control, I think I'll try to get that one picture up there. Yeah, see if I could just.
Yes.
Yes. Okay. See, this is what I should have done to begin with. This is the other batch of folks who've built their own. All right, so I'll stop there. If you'd like to get together and talk about this stuff, I'm happy to do it. Ben asked me to talk about the REPACS cluster. I didn't put them into some slides, but I can pull up some pictures of it. Is that sharing? Okay. So this is the Gleam facility. I'm going to give Ben a visitor from out of town tour. This is some of the HPCC staff who've helped with this project, one of our grad students. And this is the cluster inside of that building you just saw, which is at solar slash wind slash generator multimodal energy facility called Gleam. We got an NSF grant to build this cluster and to put it out there at this partially renewable energy powered facility. It just benchmarked at about 2 petaflops, which is approximately the same as we have on site here at Texas Tech. The goal is actually to explore remote management of data centers. So here's them putting it together. All this equipment that you see in a main cluster, it typically requires a whole lot of hands-on in and out, intervention to run. And here's the Dell technicians cabling it up. And you can see the electrical equipment of this switchgear that switches between grid power and solar and battery and generator, and eventually we hope wind. This is all part of the facility out there. What we did was we shoved a cluster into that facility. The goal is not strictly to, let me show you the inside of it. All right, so here's again the cluster in its enclosure. We have this is the cool aisle. Those are in between each rack, and the next rack is a thing called an in-row cooler. So it's just an air conditioner shoved in the rack. Pulls the hot air from the back of the nodes, cools it, and shoves it back into the front of the nodes, all inside this enclosure. And this enclosure is inside this facility that we talked about. And this facility has many different types of electrical power. So, for example, here's the power curve when we were testing. That's the draw of the facility, and you see the sun come up, and oh, look at that, we're getting most of our electricity from the sun. This is partial power run, and it's also partial solar array run. We're going to add to the solar array, but the goal is not strictly to just draw all our energy from renewable sources. That's mostly a cost thing. The goal of the facility is to study and explore remote management of data centers so that we can do all of the management of these clusters without having to go in and out of the machine room all the time. And that will allow us to take better advantage of the electricity that's out there. It's the UPS. So for UPSs and cooling and the in-row coolers I mentioned, and all the cabling and all that stuff, we want to figure out how to run all of that remotely. It's a 5-year research project, and the goal of the project is really remote data center control. And one of the possible side effects of this is that we can do a better job of teaching people how data centers run. So one thing I have talked with Van about, and I'm very interested in pursuing, is some sort of data center education program. We could write a grant, maybe based on BRICS, that takes the things that we've just talked about, the little hands-on computers, and couples it with some real-world experience with some large-scale computers, and couples that with energy management, remote data center management. We could write a very nice proposal, either to private industry or the government. And these days, it's good to have both options. Or even just as an educational program to be developed on data center control and management. And the purpose of this project I've shown you is to be able to do everything remotely, because if you can do that, then you can just stick the data centers anywhere you can find electricity. We don't want it, again, like the clusters, we don't want it to be unique. We don't want it to be the only way to do it. We want to show how to do it so that people can do what we're doing at whatever wind farm or hydroelectric plant or nuclear plant or whatever that they've got, that you can just stick the data center run remotely. And if you think data centers run remotely, they do not. Even the big large scale ones. The only reason that the big large scale AI farms can minimize the number of people that they have is that they let equipment die and they just tag it out and they build for a single job. Unlike an HPC cluster, which has maybe hundreds of different scientific applications on it, most of those big commercial facilities, data center facilities, run one job, one workflow, and they don't vary it a lot. Maybe they do version upgrades, but it's not like running a scientific facility out in the countryside. We want to learn to do that because we think we can lower the cost of scientific computing, improve the robustness, and even if you are just using it on campus, you'd much rather be able to do it from your desktop than have to walk over to the machine room anyway, right? So everybody wins if we can get this stuff. And I think it starts from teaching people how clusters work and try to get them to the point. And everything I showed you, Power over Ethernet remote control can be run remotely. And keep in mind that our original purpose in exploring single board computers was instrumentation in machine rooms. So all of these things go together and they're all part of a vision that says, let's make things more robust, more reliable, more possible to run remotely, more easy to understand, more amenable to open source and not proprietary solutions, more teachable. All right, I should really stop because you guys only have 10 minutes left in your meeting and I've kind of dominated it up to now.
Well, I mean, that was a purpose for inviting you, so I don't have to talk.
So please go do that. If you have questions, ask us. I've got a whole bunch of smart people who know how to do this now.
Well, one of the things that I've been playing with in the last week or so is I've set up and configured a virtual cluster using Proxmox. I've got it up. I've got it booting nodes. My next step is to go ahead and install SPAC and then some software. I'm doing this in order to model the software that I'm going to be using on the SPC BRICS cluster that I got the hardware.
That's great. Oh, Van, could you do me a favor? Could you invite all the graduate students from Texas Tech who were on this call and postdocs to please come visit your equipment that you got donated from
Sure.
Tech? And then you folks help Van turn it into a cluster, okay?
Sure. Open invitation. Just give me a call and I'll meet you out there.
It's just the other side of the airfield from us. Any questions? Well, thanks for inviting me. I really enjoyed that, and I apologize we're talking your ear off, but it's just I'm excited about this stuff.
It was good. Are there any questions before we let Dr. Sill go?
in the main center, you said they were Dell servers that are making up those clusters?
Yeah, almost all of our equipment on campus is Dell, and then the equipment that's out at Reese that I showed you, which is considerably newer than my current equipment on campus, is Dell too. And I will say that we don't treat them as favorites. We always bid everything, and all I will tell you is that Dell really wants our business, and they work hard to get it. And I turn that into discounts as much as I can.
That's great. We did something similar in New Mexico at University of New Mexico. I don't know if you remember that back when the governor. So then we had clustered NVIDIA desktops in each one of the schools, and I was at Eastern New Mexico University in Ruidoso, the Branch Community College, and so that worked really well. We've talked about this before in some of our BRICS things. The problem we had is nobody taught us how to use the stuff right, and that's why it all went away there in New Mexico. So hopefully, you're going to have the right training and whatnot in there, and like you said, and the data centers. I'm retired from Exxon Mobil, and I was in the data center management in Houston, and that is something that would really be awesome. I'm really kind of excited about what you're doing there.
Mm-hmm. Well, there's a big need that they can't get enough people who know how data centers run.
Right.
And
oh yeah.
I will say, as excited as I am about the stuff I showed you, if you take a peek at some of how they're building the big AI machines, it's as much of a leap beyond where we are at the clusters that we run for Texas Tech as those clusters are above the single board computer clusters that I showed you. Those AI special built machines, never mind cabling up the things to the back, the whole back bus of the whole rack, cooling outlets and all, you just plug the nodes into. It's built at the rack scale. It's really astonishing stuff.
Wow.
So there's a Serve the Home video just out about this. If you look it up, it's Serve the Home is this. It doesn't have anything to do with serving the home. This guy got way over his skis and has a major business exploring the state of the art of computing. It's Patrick Kennedy, and he just has a video out about Dell's factory where it makes AI factories. You can probably search on that and find it. It's astonishing thing.
Great. I'll look that up. Thank you.
But yeah, there are jobs at data centers, and I've been pushing my own son to learn it. So
yeah, it's great.
Yeah, I sent some single board computers to my grandkids.
Yeah.
So
as for the problem you mentioned,
oldest have already latched onto them and are playing with them.
Yeah. So if they can get past the problem that Stephen mentioned, I call it the new telescope problem, because I used to teach astronomy for a long time, and we would have open observing nights, and pretty much every weekend or every other weekend, some parent would come by with especially around the holidays, they'd bought their kid a new telescope, and honest to God, they didn't know where to point it. And it'd show up. Sometimes it'd literally be upside down, we'd turn it back right, set up for them, and then we'd get it, say, okay, it's all ready to go, and they would step back and, where do you point it? And this is a very common, it's exactly the thing that you mentioned. I've got my computer running. What do I do with it? So I think this is something we need to think harder about, but I don't have great solutions myself. Maybe the students will come up with some.
Well, I'm hoping.
We did start. We started a GitHub repository. Daniel, didn't we? Yeah, that link. It's it's like a very small collection of HPC software. We found that the biggest problem is there's a huge collections of HPC software, and it doesn't solve the new telescope problem. Anyway, so we wanted to build a small repository of getting started examples, like do this and it will work. Here's how to run a simple GROMACS problem. Here's how to run, a large language model. Here's how to run. Well, we can't use the proprietary stuff, but any one of a number of sort of standard codes, but just enough of it, right? Not the whole tutorial. Like, here's a little sampler, a little box of chocolates of HPC problems. Oh, he's put the link in the chat there. Simple HPC benchmarking. Thank you, Daniel.
So I believe you've sent your PowerPoints to Jessica, right?
Yeah, please get the latest
We'll
ones.
upload those to the our website. I forget what it's called now.
Yeah, I apologize for the size. The PDF is smaller, but the PowerPoint, it always blows everything up by a factor of 2.
Van, I stuck the BRICS summer workshop in there. Some of your audience may be interested in that workshop that's coming up. It's the main BRICS thing, but especially some of the discussion we've had in planning that workshop is around the training part of using supercomputing. So anyway, if you can, they're offering stipends for that as well. So just if you want, you can check it out anyway.
Yeah, and for the Texas Tech folks, if you haven't gotten involved in this kind of outreach stuff, it is enormously fun. Just think of the fact that somebody taught you how to do it. So you should go teach other people how to do it.
Yeah, and that's why we work at universities, for education. Definitely not for the paycheck.
Yeah, I'm going to put a link in the chat for the latest PDF of the slides too.
Okay, well, if there are no more questions, I'm going to thank Alan and call this meeting a close.
Thanks so much.
All right.
Great. Thank you.
Thank you, everyone.
Thank you.